Good morning, folks, and welcome to Sanders Amps and Seymour Duncan 8440. Channel selector, effects loop, reverb, overdrive channel. By all accounts, these get good reports, these amps. We've got 4 EL84s in there, 2 10-inch speakers, choice of speaker output, ohm rating, and there's our tube layout. So people seem to like these amps. This came in because the owner is, it needs a service. It's got scratchy pots, plus what he describes as a whooshing sound intermittently. So first things first, I'm going to take a look at the schematic. Okay, so there's quite a lot going on in this schematic. I'm not going to attempt to describe every detail of it. I'm just going to go through, point out the most obvious features. Sometimes it can take a lot of pretty in-depth analysis to understand exactly why a circuit has been designed the way it has. So really, in approaching a schematic, I'm interested in what that circuit does maybe, or what this circuit does, or this, but always breaking it down into sections. And there are some very obvious sections here, right? We've got our power filtering down here. And as we look at it, it is diode rectification, bridge rectification, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There is a lot of capacitance going on in here. Some of this looks like it's capacitor for the bias. We'll figure that out in a while. Down here it looks like we have our basic power filtering. Up here we have our input. Signal, of course, is going to come all the way through here and then down through here. Up here we've got our reverb send and our reverb return. Here we have an effects send, effects return, as we just saw there on the front panel for easy access, kind of a nice feature. And of course here's our power section with our 4 EL84s. And they're calling it an 8440, so I'm going to assume this is a 40 watter. 10 watts perhaps per power tube. So what do we have up here? We have V1, our V1 situation, 12AX7, V1A, V1B. Tiny little writing, so I don't know if you can follow this, but some of this is pretty standard, and if you've ever looked at a Fender schematic, you'll see some similarities. We've got a tone stack, which is pretty much the same as a Fender treble mid bass stack. We've got our treble, bass, mid, 3 pots. We've got 220 picofarad up here, 100K slope resistor, a 0.1 UF and a 0.047 UF. I mean, almost identical to our Fender. We have a bypass bright here. So we've got our signal coming in, comes up through a 0.1 UF coupling cap, down into a volume or gain knob here, allowing the signals through to our tone stack. But we have a switching arrangement here where the signal can simply bypass this, which ultimately would just be like turning this up full volume. So that means that if this is cranked, we must have another volume somewhere in here, and as we come along we see, okay, here's another volume pot, a 250K here. So if this is being cranked so that this signal coming through is maximum and overdriving the next stage, then we're controlling what happens after that with this volume pot. A little bypass cap here is a bright cap. There's gain boosts all over the place. We've got our typical triode stage here with the plate resistor, the signal grid, and the cathode. And here we have a 1K with a 22 UF. So our cathode resistor is a 1K. But we can switch in 47K of extra, and that'll give us a considerable gain boost here. There's a relationship between what goes on with voltages here and the amount of current that passes through the tube. And you often see in gain stages, if you look at any Marshall gain stage, in the gain channel, they'll have anything maybe from a 10K to a 30 or 40K in here. And that gives us much more current to drive through to the next stage. So there's our aforementioned volume coming down here into our next signal grid. Here again, we've got more gain boosting, repeating this technique here, just boosting the amount of resistance on the cathode. I can't quite read what that says. 1 watt, 1 meg, I can't tell, it's too tiny. And then we're off to the races here. I'm not going to get into all of this, but we've got solid state circuits here to drive the reverb and for the reverb recovery. And there's our reverb control coming in. Pretty simple circuit here for effect send and return. It looks like they've got a buffer here. This is a transistor, right? The symbol for a transistor, as are these. We'll be coming back in here. There's our grid leak resistor to ground, 200K. And here we have phase inverter. Almost looks like a long tail pair the way it's set up, but it looks like we have a DC coupled stage here. We have no capacitor to block the DC that's coming in. So this is called DC coupling. And so there's an interesting relationship going on here, but we've got two sides of the same tube, V3A and V3B, and that's a 12AX7. And here we have our power section. We've got our cathodes. These little symbols are our filaments, so we can ignore them for the time being, assuming that they're working okay. But we have a cathodes here, and they're tied here. Coming down through here, through a 10 ohm, 4 watt resistor. 10 ohm, interesting choice. Sometimes you might see a low level resistor here so that you can get a reading on voltages to determine plate current. However, this is not cathode biasing by any means. You'd need a lot more than 10 ohms to cathode bias this. And we see that these are connecting up, coming down through this is in fact the grid leak resistor here, and there is our bias. And here we see it down here coming into a 10K pot, so we can bias this to make it hotter or cooler. And then if we follow this back here, we will see that it is a tap of our rectification. Okay, so now we have a general idea of what's going on. There's one more thing to look at perhaps here. We see a 12 volt system here. Green LED, channel select. So this is most likely a relay, some kind of a relay system going on in here for foot switch channel switching, and it's being run off 12 volts. That means that there has to be a 12 volt system, and if we look over here we see 12 volts, and we see that this system here is designed to supply 12 volts to our channel switching relays. And that's pretty common. You have little electromagnetic switches in many amps for the foot switch channel switching. And so we have crackling in the pots. Well, that's an easy thing to service, relatively. Let's go take another look at the amp, and we'll pull that chassis out of there and see what we can see on the inside and see what it is that could be creating a whooshing sound. My guess, to some extent, my preliminary guess, is that there is a lot of capacitance going on in here, and this amp is down here, it says in the fine print, March 1990. That makes it 33 years old. This amp, probably some electrolytic caps are due for replacement. But let's go take a look, see if we can reproduce that symptom. Okay, just fired it up for the first time. Sounds like a rainstorm is going on in there. Kind of interesting. No indicator light over here showing on or off. Okay, we've got a light indicating channel switching. Missing a lock nut on here for a foot switch. These are loose too, so there could be problems on the board in there. See, it's moving around. Not sure what's going on. I've got the volume turned all the way down. Ooh, that doesn't sound good. Ghosts in the machine. Okay, enough of that. So we have the usual suspects here. EL84s. Looks like made by some company called RAM. RAM. RAM Works. RAM Tubex. Anyway. They don't look like they owe anybody anything. They look like they've seen better days. Paint's pretty much all burned off. So I'll put them on the tube tester. Couple of JJ 12AX7s and what I'm going to assume is a 12AX7. But when they haven't even bothered marking it or labeling it. Anyway, we'll put them on the tube tester, see what it tells us. A quick bit of background on my tube tester. This ICO model 667 was discontinued in the early 70s, I believe. And this one is mint condition. I got very lucky, bought it off a guy on eBay, and it looked like it had never been used. I think I paid about $550 or something cash. And very fortunately for me, he lived down in LA and I'm up here near Santa Barbara, so I just zoomed down, grabbed it, and it's nice to have a really nice working model of one of these. So let's see what the Oracle tells us about our tubes. First, we're going to look for a 6BQ5, otherwise known as an EL84. 6B, come on, gotta be in there, so there we go, 6BQ5. So it's telling us the filaments are 6.3 and I want to set these knobs to certain settings. These things are really confusing when you first look at them, but actually they're very simple. So I've got a little reminder here, always start at 0. If you put this up too high, you can burn out your filaments if you have too much voltage going through your filaments. But anyway, these are 6BQ5, so 6.3 volts. It's telling us also 60 and 95, grid and plate. 60, 95. And then it's telling us where to set all these levers. Now, these levers are basically just routing everything inside here because each tube, of course, has different pin out. So what this is doing is setting up the pin out. So I'm not going to drag you through all of that. Suffice it to say that it tells me what to do exactly here. Well, let me just go ahead and do it. 6, 5. Okay, got it plugged in, powered up. turn up the voltage inside the amp. This little, we're looking at 120 volts, 125, 115. Really I've got a button over here. You press the button and you turn that knob until you get it right in the center. So we're kind of calibrating the voltage. My tube in the correct tube socket. My instructions here tell me that merit, we're talking about the plate, how much oomph we've got in our plate. Okay, 7, press number 7. It's got some, but it's getting pretty tired. This is a pretty tired tube. It's still working. Okay, everything's set up. I can just go through each one, plug them in here, see what we get. It's going to take a minute to heat up the heater in there, and we will see that needle come up when the heater is heated up. It's sitting pretty loose in the socket here, so I'm not sure what's going on there. Okay, there's something starting to happen. Took a long time for that heater to warm up. Now we press 7 for our plate, pull on the merit lever. Still heating up. Let's give it a second. Not getting a lot out of this. It's not a very good tube. Not as good as the last one. I wasn't expecting much. You know, tubes do get old. I used to quite often use old tubes that I found in radiograms when I was doing rebuilds. And I learnt the hard way after, this is back when I was just starting to build, you know, I just was kind of cheap. I'd use whatever was handy. But I would find myself analyzing tube circuits and tearing them apart. And really all the time it was just actually the tube was half dead or had noise in it or whatever. These are taking a long time to heat up. Ding, 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 ding. Ding, do, 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 do. Okay, it's not leaking. Go to the plate, let's see what happens. Plate seems dead as a doorknob. They're past their use by date. That's all I can tell you. They're tired, they're old, they've clearly had a lot of working life. And so the first place to look is always the most obvious. Yeah, this customer is in for a new set of EL84s. Well, surprisingly, a couple of the 12AX7s were really subpar. This one has one side on it that's pretty much dead, and this one just tested weak. And so what you'll end up with if you don't replace these is you'll end up with an amplifier that's not very sparkly, not very bright, has early breakup, might have some noise, maybe some microphonics, but really the amp's just never going to sound as good, and so consequently you won't sound as good. So they got to go as well, a whole new set of tubes. There is one here that tested good both sides, so clearly we'll keep that. Now let's pull this chassis out of the box and see what Most of the time when I'm pulling an amplifier out of the box, I'll turn it on its side, whichever way the most weight is down here at the bottom. So that as I'm sliding this out, I'm not worried about something tipping over from the top. It's just much easier to manage. And as I look at this, I can see that these are chewed out here. There was no backing plate on here when I received this amp. And these are seriously chewed out, which means somebody's been taking these off and on in a haphazard fashion, and who knows, maybe they've even been inside the amp already. So the screws are out, but with the weight on the bottom, it doesn't want to fall over or do any damage. Well, first, most obvious thing, the output transformer is just hanging loose. Looks like some bolts fell out of here, or maybe it was, it looks like it was bolted in. It's hard to tell, but it was never, I mean, how does that come unbolted? I don't know. Anyway, moving along. Inspected by someone, we don't know who, but I don't see any bulging on those caps. Inspected when? Who knows? I don't see any bulging really on any of these caps. So that's interesting. So if there was something really obvious in here, apart from this, if there was something really obvious in terms of there was bulging caps, or, you know, I'm looking for any kind of burnt resistor, anything in the circuit that doesn't look happy, then that would give me reason to pull this board out. But for now, if I don't see anything like that, I'm going to talk to the client and talk to him about putting in a new set of tubes, which he will have to spring for before we go any further. I'll bolt this back in place, of course, but who knows? We put some tubes in and give the amp a servicing, and maybe it's as good as gold. There's no point hunting for boogie monsters if there aren't any in there. So, and I'm not seeing anything in here that's particularly egregious. It looks like, so here we're looking at soldering joints for the tubes, and they look really solid. I mean, sometimes the soldering joints on boards like this can look really sketchy, but they look really solid, so that's nice. This is our switching relay in here. You can see how it's shows you how it's switching back and forth. We've got a positive side and a negative side for the I think we said it was 12 volt coming in here, and operating this. They can, you know, operate from 5 to 12 volts in there usually. And then we come to this. So this one's gone. This was loose, I tightened it. This was broken, turns out. It was just sitting there but broken. And so the problem with plastic washers, plastic nuts, and is of course that's going right onto the board. And that means that any time a jack is plugged in or out of that, it's going to move that. And then we're going to have broken solder joints on the board and a foot switch that doesn't work, etc., etc. So I will also recommend to the owner that we put in some switchcraft jacks in there. A few other things to notice. Some of these screws are pretty loose, so just going to tighten them up. I guess just the heat in here and the expansion and contraction has made them looser than we want them. Okay, so we have a 10 ohm resistor in here. And when we look on our schematic, you can see that this is tied into all this wiring that's coming to the power tubes. So and right there, that's our little bias pot. So when we look at this, we're looking for a 10 watt resistor, and there it is tied into the cathodes. And we can do a voltage drop reading across there to check the bias. Right now I'm just going to get some plate voltage readings off the plates of each of my tubes. Now these are my temporary tubes, so I don't expect the readings to match perfectly, but it'll give me an idea of where how far out the bias might be, generally speaking. As any good amp tech will tell you, when you're firing up an amp on your workbench and it's exposed like this, we're talking hundreds of volts, maybe 400 to 500 volts in some cases, sometimes more. So it all has to be treated with the greatest of respect. So I'm just going to check my plate voltages on my power tubes here to see what's going on. Okay, looking on my chart, we see that the plate is the pin 7, the screen grid is pin 9. So I'm going to check pin 7 on each of my plates here. 540. Very high. 541 on there. 540. 539. 539. Okay, so we've got some very hot plates here, 540 volts. That's much higher than you'd normally want. So I will get my data sheet out for EL64s, EL84s rather. 6BQ5. Typically they want 250 to 350 volts. I'm just going to shut this off for a minute until I check this, because I don't want to fry they're not, they're old used tubes, but I don't want to fry them unnecessarily. Looking at my data sheet book here, maximum ratings, plate voltage 300, and here we've got 500. Now, let's keep reading a little bit. Class A, Class AB, push-pull. Nobody's exceeding 300. Now, guitar manufacturers, I should say guitar amplifier manufacturers, are quite often happy to exceed the ratings put out by the manufacturers. Fender did it all the time. It seems like, quite often cranking up the voltages. Not necessarily exceeding the specs, but running at the high end of things. So here at 540 volts on the plates, we are way hot. So this means either the bias is running way too hot, let's hope it's as simple as that, or there could be something further amiss in part of our circuitry here. So I'm pretty surprised at what I consider an excessively high voltage on the plates up here, 540. And if we have a look at what is feeding the plates, we see of course that it's coming off the output transformer here, and we've got 550 volts going up. I find usually an output transformer will drop somewhere in the vicinity of 10 to 15 volts depending on the design. So that kind of makes sense. We're 550 here coming in, there's some DC resistance coming through the coils, and so we're going to end up with 540 or so on the plates. So this looks intentional. Now of course, extra high voltage on plates in guitar amplifiers quite often makes the amp really sing, but at a certain point it can also kind of clamp down on tone. So I just want to check. So a quick bit of research confirms that yes, Seymour Duncan designed this amp to run with about 545 volts on the plates. So the next thing to consider is the bias. We've got 600 millivolts here across our, let me show you on the schematic here. We've got 600 millivolts. We've got a 10 ohm resistor here, which I've showed you. So there are two things involved in this bias. We've got our 10 ohm resistor here coming off the cathodes of the 4 power tubes, and we have a little 10K bias pot, which is that tiny little yellow thing in there. Kind of small, but if it works, it works. And we're reading the voltage drop, and it tells us we're getting a 0.6 of a volt voltage drop. So we want to get the idle dissipation around 8 to 9 watts. We've got We're looking for 600 millivolts here on our bias. across our 10K pot. So we want about 15 milliamps per tube, and we've got 4 tubes. So about 60 milliamps through the 10 ohm cathode resistor, so 0.6 volts, in other words. And so we are sitting quite happily at that. Voltages are good, they're stable. So I am not too worried about putting in a new set of tubes. I wanted to check the voltages on this and check the bias, because the price of tubes has become quite expensive. So for a set of 4 6BQ5s, it's not too hard to pay $100 for a set of 4 power tubes. And I didn't want to put them in there and then have the owner come back and say, you know, my amp's fried the tube. So I just spoke to the client. He's a happy camper for a set of new tubes. He's going to have a good sounding amp. He's not going to bother about these jack replacements at the moment. He just wants to take it and try it out, see how he likes it. And so, happy ending to this story. Thanks for watching.